So in today's lesson, we're learning more about our solar system. First of all, we look at a historical perspective of what people thought about our solar system in terms of how it was organized, how things moved, etc. The important people in today's lesson are Copernicus, Tycho Brahe, Johann Kepler, and Galileo. So we want to go back to what the first popular accepted model of the solar system was. You might have been surprised to hear that that one was a geocentric model. Geocentric means that everyone believed that the Earth was at the center of our solar system and all the other planets, including the Moon and also the Sun, orbited around the Earth. Well, part of the reason for this is that this model of the solar system was not arrived at in a scientific manner. It was based on observations, but there was no testing of ideas. So if you think back to the lesson on science and pseudoscience, you should see that or recognize that we're not using a scientific approach. We are looking at observations, but we're not testing to see if our ideas match observations or if there's anything that contradicts those ideas. And another thing that made this model popular and also unscientific was that it was really embraced more for philosophical reasons than scientific reasons. There was some belief that the Earth was not perfect because humans weren't perfect, but all the other bodies that we observed in the sky, which were referred to as heavenly bodies, were perfect, and so they were sort of able to move in different ways while the Earth was not able to move in the same way because it was sort of classified in a different way. Most of our ideas that we think about with respect to this geocentric model could be traced back to the ancient Greeks, and we're going to put a lot of the blame on Aristotle. Aristotle was a famous philosopher, but he didn't approach things scientifically, so he came up with a lot of ideas that really weren't able to be tested or were just really sort of accepted as true without any sort of verification in a scientific manner. So what are some of the observations and beliefs that contributed to this geocentric model? Well, first of all, there was a basic inability to believe that the Earth was moving. And we really can't be too hard on ancient people because of this. Think about your everyday experience. Do you have any way to prove that the Earth is moving? You go outside and you would think that if the Earth was rotating as fast as it is and moving around the sun as fast as it is, that in some way you would be able to detect it, but we know that that's not true. So the fact that they couldn't really sort of verify that the Earth was moving led them to believe that the Earth was stationary. And going back to this idea of the perfect heavenly bodies that I mentioned a few minutes ago, they believed that because Earth was sort of influenced by the imperfect humans that lived on it, all the other objects that they observed in the sky were perfect. And so they got to move in perfect ways. They got to move in the most perfect shape, which was the circle, and also at constant speeds. These were ideas that originated with Plato and also further advocated by Aristotle. We're going to see that this idea of constant speeds and circular motions is going to really stay with the models of the solar system for a long time, even after scientific approaches start being used. Incredibly, the geocentric model of the solar system was advocated by Aristotle was accepted in the Western world for nearly 2,000 years. As we get to the time when the scientific approach is starting to become more popular, which was a contribution of the ancient Greeks, we saw that people started to want to explain nature, but they didn't want to use supernatural explanations. There was sort of a starting of the division of science and non-science. They debated with each other and challenged each other's ideas. This isn't really so much scientific anymore, but it's sort of the beginning of it in that, it would eventually lead to the idea of doing experiments. And we also saw people starting to use mathematics to help develop their ideas. And eventually they would create models. We've talked about models already. Remember, the celestial sphere is a model. And these models could help to explain the physical world that they were observing. So if we think about this more modern scientific approach, there are sort of two issues where they took a very scientific approach, and it did sort of have some influence on the ideas that people had about the solar system. First, they wanted to match what they had observed as retrograde motion of some of the planets, and we'll take a minute to look at that. And I'm also going to upload a really short video of that you can use through Mastering Astronomy to explain this retrograde motion. And the other thing that people understood as they started to really think about the two different models of the solar system, that is a geocentric model where the Earth was at the center versus a heliocentric model, which is the one we have today with the Sun at the center. They understood that if the Earth was moving, we should observe stellar parallax. So retrograde motion was something that people started to observe in the sky, and they were trying to figure out how they could explain it. In this picture here, we see the path of Jupiter across the sky over a period of time. And we notice it's generally moving in one direction, but for a period of time, it actually reverses direction before it turns around and proceeds in the normal way again. Sorry about that. So the backwards motion is what we refer to as the retrograde motion. And scientifically, they understood that they needed to explain why this would happen. This actually could be observed in any of the planets that were visible to the naked eye, which would go up to Saturn, that were further from the Sun than the Earth. Of course, because they were still working with a geocentric model, that statement didn't really apply, but they did observe it with Mars, Jupiter, and Saturn. What we'll see in the little video that I'll also upload for you is that retrograde motion is just a consequence of relative motion. As I said, the planets that are further from the Sun can be observed to sort of appear to turn around and go backwards for a short period of time. And this is really because of the relative motion between the Earth and that planet. So the people in the blue shirts here represent the path of the Earth, and the people in the red shirts would represent a path of a planet, say Mars. And what happens as the Earth is approaching Mars, as long as Mars is ahead of it, it appears to move in the normal direction across the sky. But as Earth catches up to Mars and starts to pass it, Mars appears to go backwards. That's actually sort of like when you're on the highway and you pass a car that's going slower than you. Relative to you, that car appears to be going backwards. You know it's not going backwards, but it's the relative motion between yourself and the other car. So that's what happened with retrograde motion. Now, stellar parallax is a little bit more complicated. But people understood that if the Earth was actually moving, as it would change its position in the sky relative to the Sun, we should also see sort of relative motion of nearby stars. Parallax is when something close to you appears to be shifting across against a background of further objects, but it's not actually caused by the motion of the nearby object, it's actually you, the observer. So if you hold your thumb out in front of you at arm's length and look at it with your right eye and then your left eye, so if you sort of switch eyes, which one eye is closed, notice that your thumb will appear to move back and forth when you look at it in the background of the rest of the room. That's parallax. So in stellar parallax, what we're thinking about is a star that's relatively close to us and where it appears to be relative to stars that are further away. So in this picture here, we see the nearby star and the distant stars, and then we see where the star appears to be in 2 different times of the year when the Earth would be at opposite ends of its orbit. So in January, we're looking at the star from this angle, and so the star appears to be right here against the background of stars. If we switch our position of observation to July, which is at the other side of the orbit, notice we're looking at it from a totally different angle, and the star has moved over here. So that is what we mean by stellar parallax. So the idea was that if the Earth was really moving, why don't we observe any sort of relative motion between the stars in the sky, which would be stellar parallax? It's sort of an interesting thing that happened. Stellar parallax actually does occur because indeed the Earth is moving. However, it's only visible if you have a telescope because it's a very subtle motion. Because the shift of the star is so small that you can't even see it unless you have a telescope. We're going to stop right now, and I'll continue in the next video talking about Ptolemy.